Okay, everyone, I think we're going to get started. Welcome, everyone, to the last session. This is Global Tropospheric Reactive Nitrogen, Sources, Chemistry, Fate, and Impacts. So I think we will get started. Each person has 8 minutes plus 2 minutes for questions. So we will get started with our first talk, which is Ishir Dutta. Yes, thank you.
There you go. Thanks. All right, looks to be okay. Can I put this here?
Yeah, sure.
Perfect. Just in case I have to take notes. All right. Ooh, there's an extra cable here. Can I? There we go. Everyone, can my cursor be hidden? Okay. Hi, everyone. My name's Ishir. I'm a final year grad student working with Colette Heald at MIT. And I'm really stoked to talk to you today about some of the work we've been doing over the past year or so, trying to characterize a global tropospheric budget for reactive oxidized nitrogen, NOI. And I'd just like to thank the NSF for its support of this project, and all of you. There are more people in this room than I thought there would be for Friday afternoon, so I'm very grateful that you're here. I'll start with this figure that I pulled from Kroll et al. That does quite a nice job, I think, of summarizing tropospheric chemistry. Given that I'm the first talk, I'm going to take the liberty of spelling out why we care. We obviously are currently talking about the top left of this figure, which is reactive nitrogen, NOx, and then one representative reservoir species, HNO3. And we know that NOx is a super important driver of secondary chemistry in the troposphere, whether it's for ozone, shown in the top left, or the sort of complex cascade of chemistry that leads to PM on the right-hand side. And therefore, I think it's worthwhile to spend the time to characterize sources, sinks, budgets, burdens, lifetimes, so on and so forth, which is what motivated our work here today. I went back in time a little bit, so I'm going to spend some time on history. I pulled these couple tables from one of Jennifer Logan's papers from about 40 years ago, and she led the first study that did some of this work. And it's a really beautiful sequence of papers through the 80s. I recommend reading them. On the left-hand side, I've pulled a table that shows global sources of NOx, so both anthropogenic, as fossil fuel combustion, and natural sources, which we sort of now commonly understand, right? Like there's fires, there's lightning, there's microbial activity in soils, and it's really cool to sort of see this spelled out in a comprehensive way for the first time. On the right-hand side, I've put some dry deposition estimates, which are, our physical losses, and I just note 4 key NOI species, so NO, NO2, which form NOx, and then 2 reservoir species in PAN and HNO3. Some 40 years later, this is more contemporaneous work, which is from Murray et al. A couple of years ago, that shows a comparison of the NOI burdens across different atmospheric chemistry and climate models. I think this diagram is really cool, and it's for 2 reasons. One is that there's considerable variation in the burdens across models. There's like a fair bit of disagreement, and I retained the figure caption for that reason. And 2, even though it's been 40 years, the focus is still very much on these 4 key NOI species, so NO, NO2, HNO3, and PAN. And our goal with this work was to, take a step back and look at a slightly more comprehensive picture of the various, the many, many NOI species, perhaps do a better job or try and characterize some of the inner conversions and fluxes, since we've learned a fair bit in the intervening time about the chemistry. We did this using a combination of models and observations. On the modeling side, we used our favorite trusty chemical transport model, GEOS-Chem, run pretty much straight out of the box. I didn't make any drastic modifications. The only real thing that we did was to add diagnostic tracers to track every NOI reaction, which was a lot of fun over the summer. And so that gives us a sense of how nitrogen mass is moving through the system from emission to deposition and everything in between. On the measurement side, our model, we used data from ATOM for 2 reasons. 1, so that we could evaluate our model's performance more generally, and 2, that once the model provides us with a budget, we have some sort of real grounding to contextualize what that budget looks like. And I'd like to thank the lovely and talented people who worked really hard to make these NOI measurements that I can stare at 8 years later. I'll start with the measurements, and here I'm showing some stacked vertical profiles of NOI from ATOM 1, so that's summertime, northern hemisphere summertime. This is just the northern hemisphere. And I've, again, picked the 4 key NOI species, so NOx, both NO and NO2, HNO3 and PAN. On the left side, I've put observations in the saturated colors. On the right side, the model representation is in the washed out desaturated colors. And I think the model does generally a pretty good job of capturing the shape of the vertical profile. There is a slight but noticeable high bias, and a lot of that is due to a high bias in HNO3. This is not new to anyone who's run GEOS-Chem. It's a long-standing high bias. It's been the subject of much discussion, debate, and many previous studies, so I'm not going to belabor that point here. But TLDR, we do a good job of capturing the general profile. There's a slight high bias. Most of it's due to HNO3. But this is only one season, one hemisphere. Let's zoom out a little bit. And this is across atoms, so therefore across seasons, both hemispheres. And I think that general description still holds true, right? We see general shape of the profile pretty good. There is a slight high bias. It's still pretty much HNO3. You can see that pretty clearly. Pick your favorite panel, and you'll see that kind of figure. And so I think that gives us, a sense of how to think about our budget when we get it. And I'm about to put up a figure. It's a lot. This is the most comprehensive global annual NOI budget that I could put together for the troposphere. Don't try and take it all in. I'm going to break it down. We'll go through it together. If I don't talk about your favorite branch, I'm sorry, you can come find me. We can chat about it afterwards. But just to give you some context, the big blue, dark blue bubbles show NOI species burdens. The vertical arrows, there's one pretty visible one on the left-hand side in red that shows emissions. There are corresponding downward-facing vertical arrows in yellow and light blue that show wet and dry deposition. And then there are these, swirly light blue curved arrows that show chemical pathways interconverting various NOI species. And so I'm going to take a look at a few features of this figure. The first, very reassuringly, the biggest buckets on the figure are the ones that we've studied for the last 4 years, right? So that's good. We've not been looking in the wrong place. It's still NO, NO2, HNO3, and PAN. Good to know. Secondarily, one of the largest arrows, the largest fluxes on the figure is the photolytic oxidation of NO2 by OH to form HNO3, which is sort of one of our key reservoir species. And that's also great because before we started this work, we were like, okay, if we have to tag just one reaction, tag NO2 plus OH, and then that should give us a good sense of what the rest of our budget should look like. And it's obviously, it's one of the largest errors, but it's also the key loss process for NOx to form other NOI species, NOZ species. Next, of course, once you form this HNO3, it doesn't stay in the gas phase for very long, well, depending on where you are. And so this HNO3 equilibrates to form aerosol particle phase nitrates. And then together, this sort of total HNO3 nitrate system forms what we classically think of, right, as the terminal sink for NOx, or NOI. And as you can see, that's pretty much because almost all the deposition, all the physical removal is through HNO3 or nitrate. However, it couldn't be that easy, obviously. And recent work on nitrate photolysis or renoxification has sort of added some context to this chemistry. And so, I don't think it's quite right to think of the total nitrate system as a terminal sink, and instead it sort of forms a partial reservoir of NOx in some ways. And so it has kind of a dual role. And in the current model configuration, this is not trivial. The chemical flux of renoxification is comparable to the amount of nitrate that's removed through wet or dry means. And so, it's worth consideration. I'm flashing to 20 seconds. I'm about to wrap up. And so I'd like to point out that this is also not a certain process, right? There's a fair bit of uncertainty here, and so that's worth further investigation, which is currently part of our ongoing work. I think this sort of framework allows us to do two things. One is identify some key features of the NOI budget, like what is the important processes that we should go after, what are the things that we should constrain in a systematic manner. And so we're doing that with, for example, nitrate photolysis. We've done that with aerosol uptake of NO2, and we're trying to see whether we can shrink some of this disagreement between various models by a more process-oriented approach. Thank you for your attention.
Great, thank you. We've got some time for questions.
I didn't know we.
No, we don't.
Yeah.
Sorry.
Come find me afterwards. I'd love to chat.
This is coming down from E?
Yes.
Oh, did it already? Okay.
Yeah.
All right. Next up is Lingyun Meng.